Hey guys, my name is Amanda Hinchman-Dominguez. I'm a software engineer at Yellow, and welcome to Kotlin, the next frontier for modern metaprogramming. This was a talk that is a continuation of some exploratory research that I presented last year at Kotlin Conference in Amsterdam. So turns out nobody was interested in my research, but they were really interested in the project that I was developing at the time, and I'm continuing to develop today. So lucky for you guys, we're going to be talking about things that are more exciting than academics. So for those of you that are unfamiliar with TornadoFX, TornadoFX is a JavaFX framework that essentially leverages Kotlin. And it's really great for internal desktop applications. And for a while, I was using it to do the jobs that I didn't want to do. And with this particular story, I was working a job where there were 3 of us developing and maintaining the code base for about 50 other B2B clients. And as if that wasn't enough work, we are also required to create live demos about 2 to 3 times a week, and it took about 2 to 3 hours to do every time. This really killed me, so I created a programmatic wizard that essentially generated the XML that salespeople could do instead of me. And the thing about this is that I created some serialization rather than using a serialization library, and I ended up with this UI bug that was really difficult to diagnose. And in the case of this particularly nasty bug, we can see that the expected behavior here is mostly there, not all the way. It's obvious that there's this particular sequence. So because of that, I started asking people, wow, I think I need to look into some UI testing, but I have no idea how to write UI testing. And I started asking other developers, what do I need to do to be able to create UI testing? Unfortunately, every time I asked someone, I got a different technology and different answers every time. And because of that, I was like, well, I've used metaprogramming to generate code. What if I could use metaprogramming to generate UI tests? So TornadoFX Suite was kind of born out of this whole situation. And TornadoFX Suite is a project that's aimed at automating UI testing for projects, particularly in the TornadoFX framework. So let's get started with what kind of UI tests are available. We can split all testing into 2 different kinds of testing. So we have black box testing, which is essentially done from the user's perspective. You have no idea what's in the code itself. And the point of this is to test what's in the behavior and the functionality of the software, so it doesn't work. This is the part that gives you this quality assurance. And this is actually I've been in companies before where it's no testing whatsoever, and it's almost all done either by hand or by automation. Then there's also white box testing, where you test how the system works. This is usually done from the developer's perspective. You know what's in the code. And if you're a developer yourself, you're probably encouraged to write testing. When we're talking about UI testing, it's actually a little bit of a gray area. Exploring the environment of the application itself may reveal bugs, but without any white box testing, it's extremely difficult to be able to diagnose and solve those problems. So not only does UI testing help in define the desired behavior, but it also makes debugging, refactoring, and maintaining your code base a little bit easier as it grows in complexity. Now that we've kind of covered what a UI test is, let's go ahead and go into what makes a good UI test, right? Really, it's 3 simple steps. If any of you guys are Android developers, maybe you've had experience doing this with espresso testing. You grab a particular view, you perform an action on that view, and then you check to see if the UI looks as it should. How might metaprogramming start with being able to detect those views? The idea that I had kind of was a little bit philosophical, and I wanted to have this true sense of metaprogramming. So I wanted to be able to analyze the code without knowing, what's in the code before runtime. Since I'm doing this in Kotlin, I considered a few options. So the first and obvious one would be Kotlin scripting and reflection. A lot of languages have reflection. It's actually a metaprogramming capability. Ruby has it, Haskell has it, Java has it, and of course Kotlin has it. The only downside is that the strategy I went with was to basically upload the project, analyze the code, and then be able to pick it up from there. Kotlin scripting was unable to compile basically string code until about, well, it's always been able to do that, but I kind of ran short when it came to loading imports. And Kotlin's not totally mature as a language yet. It is widely used, but a lot of this is kind of testing the bounds of it. And I think only 2 weeks ago, Kotlin 1.20 came out. And I don't know, I still have to test it out, so we'll see. I went with, I tried to look into sockets and Java agents next. If anyone happens to be a JavaFX person in here, there's this really popular project called Scenic View, which was created by Jonathan Giles. I looked into his code and I was like, wow, this is really interesting. Why did you choose to go with this way? And it was kind of funny. He just kind of said, I don't know, man. I went with the way and it all sucked. Just choose a way and go with it. So I took his advice and I ended up going with AST parsing. AST stands for abstract syntax tree. So rather than analyzing the code, this is a class, this is a member, this is a method, whatever. What it's actually doing is when you analyze the code, you're looking into the data structure of the code. I ended up going with Castree and JSON. Castree is this open source library for Kotlin where it's just a wrapper for the compiler. And the really great thing about using AST parsing is it kind of helps me surpass some of the metaprogramming issues that you tend to run into with a statically typed language. So some of those challenges might include metaprogramming doesn't really respect encapsulation. Is it a private field? Is it a private class? Whatever. Or typecasting and recursion. Because the thing is, when you go into AST parsing, you can kind of see how deep the tree goes, and it's potentially infinite trees. This is where JSON comes in, and JSON is a Google library that essentially turns whatever objects you have into basically third-party JSON objects or JSON arrays. So this was really interesting for me, mostly because I was able to create an intensive recursive system in order for me to parse the data structure of the code into more than just properties and methods and constructors. But what I'm really concerned with is grabbing UI elements. And this is kind of an interesting bit because, well, it looks like the hash map got cut off there. But what I started finding is that there are patterns in certain types, and the same applies for methods and classes. What does it mean? I really don't know. I have no idea. This was just a way for me to grab UI elements. So let's get to the part that I actually care about, saving UI controls. For TornadoFX, if you have a JavaFX framework and you have certain controls, it might be text fields, it might be buttons, it might be forms. So I create this dictionary of certain elements that I care about, and I can use my AST parsing to recognize that this particular area, this is a snippet of TornadoFX code. I actually turned to it because there's so little code, and I used to hate coding, so. But yeah, you can see that there's a pattern here, and once I was able to detect, okay, this is a view, here's the root, I just start iterating down, and once it matches the part of my dictionary, essentially I'm able to save it into certain data structures called a directed graph, or a digraph. And this is the drawing that I did. I think I wasted 2 days on this because I didn't understand how a directed graph works. Always draw out, your solutions before you code it. It'll save you tears. And this is what it looks like. So This is the original. I upload a project, and it reads the code, it analyzes it with AST parsing, and this is what it looks like in the background that's printing out all the possible views. And then these are the particular elements that I care about. So cool. We have our locator mechanism down. The idea is to analyze the code without knowing what's in the code, an external code before runtime. So how can external processes be able to analyze that and then write tests and then be able to perform an action with that? So this is where our knowledge for testing actually comes in. This is phase 2 of this behemoth of a project, and it's writing tests with TestFX. TestFX is really, really similar to Espresso in that it's this really slick API that allows you to set up test applications easily, and then you can simulate these robots to basically fake actions that you wish to perform. So the great thing about TestFX is that you can use matchers to be able to grab these nodes and then verify the expected states. Because native desktop development is usually done, for internal purposes, a lot of people tend to not attach IDs to their particular UI elements. And, why would you need to? A lot of people don't even need to do testing for it. It's just done for a small thing. In my particular case, I would like to diagnose this problem that I need to do, but I don't want to force people to attach IDs. I made this interesting discovery that in testing, you can actually dynamically add IDs to your test application. I don't know, this is kind of cool on my part. So we already know what elements we have that we care about. This is kind of like a similar strategy. We can use metaprogramming to essentially just iterate down our structures and then attach randomly generated IDs to them. So I mentioned Kotlin scripting before. I threw it away for the analysis part, but it does come back when it comes to writing actual Kotlin files themselves. Nothing super interesting here. Really, this is the only thing responsible for creating the Kotlin file, and then it's a whole lot of string concatenation. This project's full of really bad ideas. But here is what it looks like when we have one simple test. This is where I simulate a fragment, and the kind of cool thing is that we actually have one test that passes and one test that fails. Wow, that text is really small. So the test that fails is actually for testing the button. It was a really, really quick playover, but this is supposed to be a model. The top one's filled, the rest are empty. And the reason why it fails brings us to this print line. We passed in some null objects. Yeah, feel free to ask. I have no idea how to do that. I am so sorry. Control plus?
Like if you turn the lights off.
Yeah, let's try that. Here's a lesson in why you should not do demonstrations of flat text. Many apologies for that. Yeah, this is a video, sadly. Sorry about that. I don't trust demos. I feel like demos never work, but I want them to. Yeah. Yeah, I do apologize about that one. But in any case, the actual issue of the whole failing test comes from the fact that we're trying to print a null item. So it's kind of useful, but not super useful because we can't actually have these tests written to verify very specific behavior. So going back to our whole, what is a UI test? We grabbed a particular view, we wrote some actions for the views that we've managed to catch, and instead of seeing to check if it looks as it should, all we've done is check to see if it changed. If any of you guys happen to watch Silicon Valley, I feel like this particular scene very eloquently describes what this project currently is. Is it a hot dog or is it not a hot dog? And as Kumail Nanjiani says in Silicon Valley, the core tech is kind of valid. We just have to train it a little bit. Here's a fun fact. Kumail Nanjiani actually went to my college, and he also studied computer science. Only he acts now, so good on him. We need better tests, but how are we going to get there? Here's a picture from when I went to Kotlin Conf. It was really exciting. It was like buzzing and all that. And one of the most exciting things that I actually got from the conference was when I was speaking to other speakers. It was like, oh wow, like your research complements my research, and my research complements your research. And I was like kind of getting this creeping feeling that it is possible that Kotlin could be another player in the next few years for data science. I'm not saying that it's going to be a huge contender or anything like that. Python does have its merits. It has packages like Panda, scikit-learn, and TensorFlow. But without the stability of having a statically typed system, being able to handle large data is not really super great for Python right now. So I do want to emphasize that Kotlin is simply not ready and not mature enough as a language. I'm not ready to talk to I don't mean any disrespect, but Pythonistas out there. I'm not trying to convince anyone that this is anything worth playing into, but I think it might be fun to just look into Kotlin as a possibility for it. And the reason why I say that is because even though it's not ready as a language, the ingredients are there. The fact that Kotlin is a statically typed language, and one of its main features is that it has a lot of null safety. It actually increases runtime stability. There's a lot of companies out there that uses statically typed languages for backends simply because it can handle large databases. And of course, Kotlin lends itself to concurrency and parallelism. It's vital for the health of data and efficiency in large software systems. And not only that, it kind of gives way for distributed systems. And the reason for this is because Kotlin exists as a functional paradigm. It encourages immutability in the code, and features like Kotlin coroutines allows developers to be able to easily implement and test this stuff. Let's go ahead and revisit where we're at in our testing. We have checked to see if the UI changes at all, but we want to check to see if the UI looks as it should. We've used metaprogramming to create dumb tests. Is it a hot dog or is it not a hot dog? So we want our test to become smarter. The criteria for a good test, of course, is to see if the UI looks as it should. But how is metaprogramming supposed to figure that out? And that leads us to our third phase, creating smarter tests. What makes a good UI test? I don't know. I only started this project. I didn't know what testing involved before that. But this is where metaprogramming gives way to deep learning. We can create an algorithm and be able to train it. And then, since I have no idea what are the components that makes a good UI test, we can send that data through different filters and analyze it step by step to be able to create predictions. And if I didn't know anything about testing, you can bet your sweet cheeks I know nothing about deep learning. In case I didn't make that clear, here's a visual of me who learns by doing. I am not a data scientist. In fact, I was really, really intimidated when I found out that this is where this ended up going, and I just went to other data scientists like Thomas Neal and Shelby Cohen, and I just panicked. I'm like, what do I do? They all taught themselves too, so it's all good. Luckily, there's some technologies out there that can help us with this stuff. Training models do require excellent hardware support and good numerics and low interpreter overhead. General learning languages, or general languages like Python and Kotlin, really don't have those features, so TensorFlow can provide them seamlessly. When we talk about using TensorFlow generally, it's used with two different libraries. You have Keras, which essentially serves as a front-end client, so we don't have to worry about those low-level operations. And then there's TensorFlow, of course, which is the deep learning computation engine. If anyone's panicking, it's all good because I'm going to try and stay away from jargon as much as possible. I personally hated using jargon. I find it to be gatekeeping and unnecessarily intimidating. And what's more, when people tend to stick to jargon, you just kind of like accept things as the truth without critically thinking about it. So when I say that, I just want to say that I want to get into what the engine actually is and how it's used with Keras. In machine learning, all data sits in some sort of dimensional space, like this crumpled paper. The core of machine learning algorithms is a means of finding transformation mechanisms that turns data into more useful representations. So we have this paper that's like given in this three-dimensional space, and we can imagine that this crumpled paper in each of its manifolds basically represents the local flatness of any dimension. And the reason why we talk about data in a 3D space and this manifold representing local dimensions is that this allows for like tensor engines to perform activities like differentiation and other calculations. So this is the essence of deep learning. I mentioned tensors before, so I'm going to back up and talk about tensors for a second. All tensors are is the key data structure for deep learning. So we can imagine that crumpled paper like the data. When we talk about tensors, all that it's doing under the hood, I know they tend to make this like really, really black box, but all it is just matrix operations. It's dot products and differentiation. The reason why I go into this is because I feel like this is one part that makes it really intimidating. Yes, there is like complication, obviously, because first of all, matrix math sucks. And then, you know, you're feeding it through different layers, and after so many, it's really hard to keep track of. But the reason why we use Keras is that we don't have to worry about all this low-level operation. So, deep learning, in my humble opinion, is obfuscated as hell. So let's start with a really easy question. Is deep learning actually learning? I spent a lot of time working in either a coffee shop or just like running the TV while working. And I'm sorry, this is one of my weird 3 AM ideas. But we're going to take this example where Peter finds out that if you smoke, you can take a break. The thing is, he doesn't know how to smoke. The deep learning life cycle can be thought of like kind of in 6 steps. So you gather and prep the data. Peter knows that you have to use some orifice to smoke a cigarette. Internally, he shapes the options in his head and then lays them out. Then you have defining the model. The model is Peter attempting to smoke, then he's using Angela's reaction to kind of like gauge the accuracy. When you compile the model, what you're doing is actually configuring your model and configuring like your weights and biases for that. The model here measures performance on training with a loss function and updates itself with some kind of optimizer. And of course, when you train the model, that's Angela's reactions and Peter like kind of like reacting to Angela's reactions. And of course, executing the model this is what deep learning is. When Peter like looks at Angela's reactions, Peter remembers his reactions and he tries to adjust his guesses. So you'll notice, in fact, when I kind of go through these steps, a lot of these steps are actually a whole lot of cross-cutting and it's really tangled together. Now, deep learning gives way to machine learning when you actually take these tensors and you end up feeding it through sequential layers. You feed the tensors through different layers, and then every single layer contains weight tensors of its own. So, in this particular example, we have 3 simple layers. The first one is the reformatting layer, where essentially it contains a set of neurons, which is the possible options that are available, and then you encode, of course, your tangled data into something that the machine can process. The hidden layer is the layer that tends to be the black box magical layer, and this is where you're performing mathematical operations to be able to transform this data. The layer is what's responsible for tensor manipulation, and it can be thought of as calculating matrices with linear equations. So we have our outputs, which is hopefully whatever it comes out to be. We have the inputs, we have a single orifice, and then we're using Angela's reaction as a weight. You'll also notice that the bias is included as part of the equation. Biases are basically made up in order for linear equations to be parameterized and modulated. The third layer is our output layer, and we have our defined neurons, and we essentially have a dictionary that says, can this orifice smoke, can it not smoke? Is it really learning? Machine learning seems to tell us that this seems to be the case, but it doesn't tell us why. So as a result, there's still a lot of room for human elements in machine learning, especially in gathering and prepping the data and also training the model. So no, it's not really learning. If you had a really, really poor quality high school education like I did, I basically breezed through high school just by memorizing patterns from practice problems and then kind of executing those patterns on the tests. And then when I got to college, especially in analysis of algorithms, that wasn't cutting it anymore. I actually failed 1 or 2 computer science classes and had to do it over again. Or in some cases, get a perfect on the exam to get a C. So the reason why I kind of went off from this project to talk about what machine learning actually is because machine learning has limitations. As a result, we've seen a lot of failures in machine learning. Uber self-driving cars, Chicago's Predpol program, which just kept sending police to areas that were notably minority neighborhoods. So a large part of this, I think, is that the wider community just needs to realize that maybe we need to get back to actual learning and not this fast meal that we've been doing. I do have some grievances with a lot of the research that I looked into, and I went through this entire explanation because jargon obfuscates meaning. It forces us to accept truths without being able to analyze what it is that we're actually doing. Furthermore, machine learning makes an emphasis on extracting away irrelevant details. This is very, very common in statistical and also economical research models. This is the part that I seem to have an issue with the most, mostly because machine learning has terms for these. You end up with overfitting and underfitting. So overfitting is when machine learning models performs worse on test data than training, mostly because there's noise in the data, and it ends up learning unwanted patterns. And then when any complexity penalizes your system, you try to regulate the data by generalizing it with underfitting. Long story short, we decide what's relevant and what's irrelevant. And the question that just keeps popping up in my head is, why do we decide what's relevant and irrelevant? I mean, are we God? Technology is only as good as we make it, and in my view, computer science is where the rules are made up and the points don't matter. So I expressed some of these thoughts to other data scientists, and turns out they're of the same mind, and I was thinking about coming up with an alternate version, well, a slightly modified version of the way machine learning works. And it turns out University of California, Berkeley had introduced this theory in 2017 in 2 different papers, curiosity-driven exploration of self-supervision and large-scale study of curiosity-driven learning. They use video games to be able to test out this theory, and the idea is instead of us deciding what the extrinsic rewards are, we allow the programs to have intrinsic rewards, which is called curiosity-driven learning. And what they found is that with intrinsic rewards, agents were basically able to generalize better in completely unexplored environments. I was really excited that this was an actual thing because this was my original proposition. Because complex problems shows that you're not going to have like an immediate reward for every action that you take, and extrinsic rewards are simply not scalable. This is my possible theory about maybe modifying my use of using TensorFlow. As I mentioned before, I don't know what makes a good UI test. I think I'm just going to create a data lake and see what pops up. And of course, we've talked about how machine learning is essentially feeding all these different factors and tensors through different sequential layers. Since I don't know in what order things could go in, my idea is to create a lot of different models and then address the sequential data and maybe compare it with traditional models. So starting with the first step, creating a data lake. Creating a data lake does the following. It models things that can be controlled by the agent itself, and then models that can't be controlled by the agent. This has been kind of like an interesting portion when I've talked to people about this particular project, this problem, and I've gotten some really interesting feedback on it. The first thought I had is the shape and the depth of the UI hierarchies, coming back to this really cool AST parsing stuff that I still don't know what it means or anything like that. I've had folks offer, like, maybe you could look into negative versus positive space in UIs. Code coverage, is there testing available? Someone said commits and contributors. I have no idea how that would be relevant, but why not, right? And then of course you'd have to shape this data into something that TensorFlow would be able to analyze. And then from the data trends that emerge, I would have to create as many different machines possible to permute this set of trends. So we can feed the model sequentially through different layers. I don't know, like this is kind of like an open theory from here. Is there still a room for human elements in curiosity-driven learning? I don't know, maybe. This idea is extremely new, and at the moment I'm looking at designing a system that I can simply observe. We also probably want to compare permutations of increasingly complex layers with traditional models and see how they stand. This is probably how we're going to be able to look into properties that might be worth testing. And in this way, I feel like this puts pressure on the design because it forces us to look into the way that things permute and vary and essentially create this like sense of flappiness. And to a point, looking into like where this flappiness occurs like might be mildly useful. So the trick with AI in relation to testing revolves around understanding the theory of error, understanding like where it is that we make cognitive mistakes when we deal with space and time complexity. And this is like where those various aspects of flappiness comes in. We can render these models of certain transformations, and it can lead the test to pass or fail. And that is like basically the only qualification that I'm measuring it against. Does the test pass or fail? I don't know what's going to affect it, but we can find out by rendering visual data with that. And when we have this visual data, we can draw lines to find decision boundaries. So from this, I'm hoping to be able to create something a little bit more useful, like property-based testing, to discover what kinds of classifications might be out there. What is out there? I have no idea, but I'm ready to find out. And if you're interested in looking into the project itself, it's still kind of a, dumpster fire. It's much more cleaned up than it was before. It's still a work in progress, but if you're interested in checking it out or even like looking into it and saying, hey, it would be a lot better if you did it this way, I'm always looking for people to contribute. And of course, I do write a lot of embarrassing tweets at 3 a.m. And then I do write a lot about my failures and walls on Medium. And sometimes cool things that I find out. So yeah, thank you for coming to my talk. I think we have a little bit of time for questions, if anyone has any. Yeah. Oh, flappiness. So that I hope I answer this shortly, but actually Cody Engel like defined flappiness really well. It's essentially when traditionally it's defined as when developers write tests that essentially like they're not testing for the right things, and what that can lead to is you writing tests and then they break, but it turns out you're not testing the right things, and then you end up wasting a lot of time just fixing tests that aren't testing the right things. So flappiness, in my view, is just kind of why I had like a bad taste towards testing in the first place, especially in some TDD-driven companies. Like, it's not all bad, obviously, but sometimes creating tests may not be useful after all, and then you end up wasting a lot more time trying to fix tests than actually writing the code or fixing bugs that you wanted to fix. I hope that was a little clearer. Yes?
Yeah, I have another one. So, on the last slide, you showed that you were categorizing like low risk test cases.
Yeah.
So I don't know if you trouble connecting with that, with the concept of which one to find good tests, because I would say good tests would fail sometimes.
Yeah, that is a good question. I am simply using the fact whether like test passes or fails, mostly just as, I guess, like a neuron that I'm going to be like measuring it against. So I think that's a really good point, the fact that, you know, maybe I'm not necessarily testing to see if it passes. It almost sounds like, in a sense, offering like test passing or failing as just like one neuron to like test against might be too simplistic for being able to track those trends, and I do agree with that. Unfortunately, I haven't personally thought as far as what can I create as like a median to be able to track those things, and that's what I'm hoping to find out with curiosity-driven learning. Just to kind of go back to that example, let's see, there we go. For example, like when we think about gaming, let's say you have AI in gaming, and then you say, if you shoot a bad guy, you get points for that. But what if there were like more steps prior to that? Or what if it was a complex game where you thought someone was a bad guy, but they were a double agent or something, and you don't get that immediate reward back? So I do agree, maybe there is a flaw in just measuring like the passing and the failing. If anything, I think the original design would simply be an intermediary step, and I'm hoping that curiosity-driven learning can expose maybe a different set of neurons that I could start measuring it against.
So this in particular, if this one is that reinforcement learning is like a feedback loop, I would say that like whether or not the test pass or fail, that could be like the reward.
Yes. Yeah, so the question was, would I be using test passing or failing as, you said, the neurons for the feedback loop?
Yeah, for the reward part, for the
Yeah. So my proposition, I think that would serve as the initial neuron set. I think there would have to be basically like far many more tensors like created like in progression to that. If anything, I think it would just be like the first step out of that, and I'm hoping to find trends that like come out of it, where if eventually like it can help me define different neurons that might be more useful. If anything, like it could be a little bit more complicated because we do want these tests to like eventually pass, right? But there is value in having our test fail. In the example that I had, where it was useful to have the test fail because it pointed out that there was a flaw in my project, I think the point of this exploration might be more than just learning how to write better tests. I would eventually like to find out trends and even like, do our tests correlate to what makes good UI experience? This project is so open-ended and greenfield that what I can only offer at this particular moment is what I think the next step should be, And I'm really hoping that those weights and trends emerge in itself, and perhaps I can have a much smarter answer.
Yeah, that's really exciting. This is more of a comment because I've seen something in the direction of NLP, like natural language processing, but not natural, like code language processing. I don't know if that would have an intersection of what you're doing this way. So I think people do take ASTs, but then kind of try to do all these methods that you see with like programmatic and stuff.
Wow, I don't know a lot about natural process languaging. I actually discovered AST parsing by accident. It just seems to be the thing that fits my criteria with, well, what I thought was going to be less work, and then it turns out I was stuck on it for 3 months, and I was like trying to toss it out with the other methods, and then it worked out. Yeah, I think eventually what I'd like to do with this AST parsing is actually separate it out from the Tornado FX thing, because it has nothing to do with the actual point of the project at all. I would like it to be usable for more projects in Kotlin. Yeah, but I would like to look more into AST parsing. There is interesting things from it. I just know nothing about it. I used it. I found a use for it. That's the story. Yeah, if anyone else has any questions, if not, I'll be chilling out. We can have a parking lot session. Thank you so much for coming to my talk.